A user clicks buy and waits. 1 second, 2, the spinner keeps spinning. 8 seconds later, the order finally confirms. Behind that click, 30 microservices just talk to each other. Authentication, product lookup, inventory, pricing, shipping, payments, a tangle of remote calls fanning out across your cluster. Somewhere in there, one service was slow, but which one? Your logs are no help. Each service writes to its own log file on its own machine with its own timestamps. You could grep for an hour and still not be sure. This is the problem distributed tracing solves. In the next 10 minutes, we'll see how one shared ID, threaded through every service call, turns this guessing game into a chart you can read in seconds. Before tracing, we had logs. Every service prints its own log lines, a timestamp, a level, a message. When something breaks, you SSH in, you grep, and you hope. The problem, logs don't compose. The gateway logged an error at 14:02:37. The pricing service logged a slow query at 14:02:37.4. Were those caused by the same user request? Maybe. Or maybe two users just happened to hit the system at the same moment. Timestamps tell you when things happened, not what caused what. Across 30 services and thousands of requests per second, the noise swamps the signal. What we really need is a way to say, these log lines, across every machine, every service, belong to the same request. We need a shared identity that travels with the work. That identity is called a trace. Here's the core trick. The first service to see a request generates a random, unique identifier, the trace ID, 128 bits, usually written in hex. That ID is attached to the request like a luggage tag. Every downstream service call carries the tag forward. When the gateway calls authentication, the tag goes with it. When authentication calls the product service, same tag. Every service writes its log lines with the trace ID included. Now the magic happens on the way out. Instead of grepping by timestamp and guessing, you filter your logs by one value, this trace ID. And suddenly, out of a billion log lines a day, you get back the dozen lines that describe this one user's click. From the first byte that hit your gateway to the last byte sent back. One ID, propagated everywhere. That's the backbone of distributed tracing. Everything else is detail. A trace ID alone gets you a pile of related log lines. To see structure, we need spans. A span is a single unit of work, an HTTP request handled, a database query run, a function that took 50 milliseconds. Each span records four things: a name, a start time, an end time, and a parent. That last field is what gives spans their power. When the gateway receives a request, it opens a root span. When it calls the authentication service, it opens a child span and stores the gateway's span ID as the child's parent. Authentication might fire off two queries in parallel. Each gets its own child span pointing back to authentication. Follow the parent pointers, and the flat pile of spans assembles itself into a tree. Every trace is a tree of spans, all sharing one trace ID, all linked by parent pointers. That's the data structure distributed tracing is built on. But wait, how does service A's trace ID actually reach service B? They're on different machines, in different processes, sharing nothing but a network. The answer is deeply unglamorous. It's an HTTP header. When service A calls service B, the tracing library adds one header to the outgoing request. The header is called traceparent, standardized by the W3C trace context spec. Its format is 4 hyphen-separated fields: a version byte, the trace ID, the parent span ID, and a flags byte. All hex, all fixed width. Service B's tracing library reads that header on the way in. It extracts the trace ID and uses the parent span ID, as you guessed it, the parent for any new span it creates. That's the entire trick. Trace ID travels in a header. Parent pointer travels in a header. No special database, no message bus, no coordination service. Just 3 extra lines in an HTTP request that every service agrees to read and write. Now we can finally answer the question the hook posed. Which of these 30 services was slow? Take every span from our trace. draw a horizontal time axis, 0 milliseconds on the left, 8,000 on the right. For each span, draw a bar from its start time to its end time. Parent spans sit on top. Children nest below. Spans that ran in parallel appear side by side, their bars overlap horizontally. Spans that ran one after another stack vertically. This is a waterfall chart, and for debugging, it is the single most valuable picture in your toolkit. Look at this trace. The gateway spans the full 8 seconds. Authentication, 50 milliseconds. Product lookup, 100. Inventory check, 80, and pricing. Pricing is 6.2 seconds long, a bar so wide it dwarfs every other span in the chart. The mystery evaporates. There's your bug. Whatever pricing is doing, that's what to look at next. No grep, no guessing, just one chart. So where do spans actually come from? Someone has to create them. There are 3 layers. First, auto-instrumentation. You import the OpenTelemetry SDK, flip a switch, and the library hooks into every HTTP client, every database driver, every RPC framework in your process. You get spans around every outbound call for free. Second, manual spans. For the interesting work, the custom business logic, the big loop, the thing you actually care about, you wrap it yourself. A single call, start a span, do the work, end the span. 10 characters of code, and it shows up in your waterfall. Third, attributes and events. A span isn't just a bar, it's a bag of key value tags. Database system, user ID, query text, response code. You attach them to the span, and later you can filter or group traces by any of them. Events are timestamped notes pinned inside a span, great for logging errors with exact causality. Most spans come for free. The valuable ones you add yourself. A busy service handles 100,000 requests a second. Each trace might contain 20 spans. That's 2 million spans per second, and you'd like to keep a week of history. You can't, you drown in storage costs. So tracing systems sample, they keep a small fraction and drop the rest. The naive approach is head sampling. At the very first service, flip a weighted coin. 1% of the time, record this trace. The other 99%, drop it before it's even built. Cheap, but dumb, you'll throw away errors and slow traces with the same probability as boring ones. The smarter approach is tail sampling. Collect every span in a buffer. Wait until the whole trace is done. Then decide, was it slow? Did anything error? If yes, keep it. If it's just a successful 100 millisecond request, drop it. Head sampling is cheap. Tail sampling is expensive, but actually keeps the traces you wanted. Most production systems run a hybrid. In production, you'll run into the same names over and over. Your services emit spans using the OpenTelemetry SDK, the industry standard protocol, often just called OTel. Those spans flow into the OpenTelemetry collector, a daemon that batches, filters, and routes them. And from the collector, traces fan out to whichever backend you like. Jaeger and Zipkin are the free, self-hosted classics. Grafana Tempo is the newer storage-focused one, built to pair with Loki and Prometheus. Honeycomb and Datadog are hosted products with slick query UIs. The breakthrough of the last few years is that you no longer pick one ecosystem. One SDK emits, one collector routes, and you can swap the backend without touching a single line of your application code. That's OpenTelemetry's real contribution. It made tracing portable. So the whole picture in 30 seconds. One random trace ID, born at the edge and carried in an HTTP header to every service it touches. Each service opens spans around the work it does, linking them to a parent. The pile of spans is rendered on a shared time axis, a waterfall, and suddenly the slow hop is a bar you can point at. That's the idea. Make causality visible. Turn debugging a distributed system from archaeology into a chart you can read in 30 seconds. If you've ever stared at 3 log files trying to guess which one caused which, you already know how much this matters. Thanks for watching State and Flow. More distributed systems deep dives on the way.